This is a walkthrough of problem 3 on exam 1 of module 9 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 3, a square wire frame of side length 10 centimeters, electrical resistance of 0.1 ohms, has a constant counterclockwise current of 5 milliamps flowing around it due to the changing magnetic field. At t equals 0, the magnetic field has a magnitude of 200 millitesla directly out of the page and is changing at a constant rate. Defining a positive field as one that is out of the page, write an expression for the external magnetic field as a function of time. That is, what is B of t? How is this magnetic field changing to produce a current of 5 milliamps counterclockwise? We have the current. We have to get the way the magnetic field is changing. The field starts 200 millitesla out of the page. It must be changing because there's a current in that loop. And the area is certainly not changing. The loop is fixed in the field. We can get the EMF from V is equal to IR. We have the current and we have the resistance. So we know the EMF is 5 times 10 to the minus 4 volts. This is the rate of change of the magnetic flux. The rate of change of the magnetic flux is d of B times A dt. The area is constant. We can pull that out of the derivative. dB dt is the rate of change of the magnetic field. We know what the area is. It's 10 by 10 centimeters, 100 square centimeters, which is 1/100th of a square meter. So now we can calculate dB dt. We get 50 millitesla per second, but we have to figure out the direction. We're just dealing with magnitudes here. What's the direction? Is the B field shrinking or growing? And we can get that by the way the current is moving. The current is counterclockwise. So in this edge, the right edge, it's going upwards. The current I is upwards. If we stick our thumb in that direction and we curl it around, we get that the B field from the current in the loop is also out of the page. So it's in the same direction as the external field. And that means the external field must be shrinking. If the external field is shrinking, then the current in the loop is going to want to add to the field. So the field must be shrinking by a rate of 50 millitesla per second. So it starts at 200 millitesla and it drops 50 millitesla every second. So the equation for the B field is 200 millitesla minus 50 millitesla per second times t. And that's problem 3.